Hello, everyone. I wanted to talk about floor function and the ceiling function for this class. It's part of 185, Discrete Math 1. So let's define these two functions. The floor function is defined to be the largest integer that is less than or equal to x. Okay. And the ceiling is the smallest integer that is greater than equal to x. If x is an integer, then you have equality. Okay, the floor and ceiling would be both equal to that integer. So let's have a look at some examples. Say the floor of half, and the largest integer that is less than equal to half would be 0, because 1 is actually greater than half. And the ceiling is the smallest integer that is greater than or equal to x. That's 1. And the floor of the 314, the largest integer that is smaller than equal to 3.14 is 3. And the ceiling is the bigger one, which is 4. So if you have an integer, then the floor and the ceiling are the same, which is that integer. You need to be careful when you have a negative number, so negative 3.14. This is actually not negative 3, it's negative 4, because negative 3 actually is greater than negative 3.14. And ceiling is negative 3. Okay, so first part, you really need to know how to find the floor and the ceiling given a number. So that's first thing you need to know. That's kind of basic knowledge you need to know. All right, now because the floor is always less than or equal to x, x is greater than or equal to n and less than n plus 1. Actually, we have that. Um, If you switch to an inequality with n, that's a little bit, we need a little bit algebra. Okay, so let's subtract n on three sides, subtract x on three sides. You have negative x less than equal to negative n, strictly less than 1 minus x. Okay, you subtract x, then you subtract n. So you really subtract x and then n. Okay. Or you add negative x and negative n. All right. So then you multiply by negative 1, you get n strictly greater than x minus 1, less than equal to x. Okay, so that's uh, the inequality. Or you can say x is greater than equal to the ceiling of x and strictly less than the ceiling of x plus 1. Or the ceiling of x is less than equal to x greater than x minus 1. All right, so let's look at this one. By that, I can define epsilon to be x minus the floor of x. Then I would get epsilon greater than equal to 0. Okay, this is always non-negative. X is greater than floor of x. And then x minus the floor of x would be strictly less than 1. Okay, you really just work with that, with this inequality. You would get this inequality. And please try to make sense out of it. Work a little bit about the algebra. So when we see a floor, normally we have this. We have a x equals the floor of x plus epsilon when epsilon is greater than or equal to 0, less than 1. Okay. Similarly, if we have the let me sort of highlight it, put them into a I don't see why it's gone. I think the shape. I think this shape is already forget about it. I'm gonna just use different color to have. All right. And similarly, we say the ceiling is n when first of all, the ceiling is always greater than equal to x, so x less than equal to n, strictly less than x plus 1. Okay. Um, and if you do some algebra, right, so subtract x, subtract n, you would get negative x less than negative n plus 1, greater than equal to negative n, and then you multiply by negative 1, you get n minus 1 is strictly less than x, it's strictly less than equal to n. So you have that. All right. This n is our ceiling. Okay, so you can rewrite it as something like a ceiling minus 1 is less than x, less than equal to the ceiling of x. Okay, so if I define epsilon to be, let's use a different one, so eta. And as a formula, this doesn't really matter. It's just use epsilon throughout. But this epsilon would be different from the previous epsilon, as some students are always confused with using the same variable in different situations and they keep writing the same variable. That's not good. Let's use eta but essentially it's just epsilon, okay? But this epsilon and this epsilon are kind of different. So that's something I want you to pay attention to. Let's use epsilon. So I define epsilon to be x minus the ceiling minus the ceiling is always bigger, the greater than equal to. So the ceiling minus x. So I can get epsilon is less than, strictly less than 1, greater than equal to 0 again. You can see from this inequality. Okay, first of all, the ceiling minus x would be greater than equal to 0. Use the right inequality, and using the left inequality, you would get x. The ceiling minus x is strictly less than 1. So we can write the ceiling of x to be x plus epsilon. Again, epsilon is greater than equal to 0, less than 1. Okay. When you try to prove equations involving ceiling and floor, usually these two equations is something you can use. Okay, so let's say, for example, want to prove that the floor of negative x equals negative of the ceiling. Okay? You can check a couple of examples, say when x equals 3.1, so negative x equals negative 3.1. So the floor of negative x would be equal to negative 4, and negative of the ceiling of x is negative of the ceiling of 3.1, which is 4, so it's negative 4. Okay. But again, examples are not a theorem, sorry, not a proof, so really needed to prove it in general situation. Okay, so here x is any real number. I'm gonna use this equation directly for negative flow of negative x. So negative x, the flow of that equals negative x, which is like x here, okay, minus epsilon. So that equals negative of x plus epsilon. X plus epsilon equals what? Equals the ceiling of x. So that's the proof. Okay. All right. Let's look at another example. Let's try to prove the ceiling of x plus n. N is an integer. Equals the ceiling of n x plus n. How can we prove that? We're gonna use this equation. The reason we use this equation is try uh, to get rid of the ceiling, so you can use algebra uh, to without those ceiling functions, floor functions. That's much easier. Okay, so we have this ceiling according to this equation. I have x plus n, which is our x here, then plus epsilon. Okay, this epsilon should be greater than or equal to 0, strictly less than 1. And then let's just switch the summation, and summation is commutative, so you do x plus epsilon plus n, okay? And x plus epsilon, when epsilon is greater than or equal to 0, less than 1, is always equal to the ceiling of x plus n. So that's the right side, we proved it. Another example. Let's try to prove and the floor of 2x plus, no, sorry, equals floor of x plus the floor of x plus 1/2 for any real number x. All right, so let's use the equation of the floor. So x equals the floor of x plus epsilon. Epsilon is greater than or equal to 0, less than 1. Okay. Oh, by the way, you can check how to get this epsilon. For example, you have 3.14, then the floor, of course, is just 3, and epsilon is 0.14. So you have a 3 plus 0.14. That's no problem. If you have a negative number, that's a bit tricky. So negative 3.14 equals the negative, the floor of negative 3.14 plus epsilon. And then you would actually have negative 4 plus epsilon. So this epsilon equals 0.86. It's still from greater than or equal to 0, less than 1, but it's actually not like 0.14. Okay, so that's something I forgot to mention earlier. Okay, so we're going to use that for x. So this one is just the floor of x, but this one, so x plus ½ equals x is the floor of x plus epsilon plus 1/2. Okay. Now, we are not sure about this because epsilon is greater than or equal to 0, less than 1. You add half is less than 3/2, greater than or equal to half. So we have trouble. It's possible at 1.2, it's possible at 0.8. If it's 0.8, then you can just get rid of it. The floor of x plus 0.8 is simply the floor of x. But if this number is 1.2, then the floor of x plus 1.2 is actually the floor of x plus 1. So this one is not very clear. So we need to work with cases. So case 1, when epsilon plus half is greater than or equal to 0 and less than 1. Okay, which is equivalent to saying that epsilon is greater than or equal to 0, less than half, strictly less than half. This is one of the cases. The second case is when epsilon plus 1/2 is greater than equal to 1 and less than 3/2. Okay, that's when epsilon is greater than equal to half, strictly less than 1. So I separate this case into two different cases. Okay, the reason is that now we can get rid of this floor to come up with something nice. So case 1, the left side, actually the right side equals the floor of x, keep it there, plus the floor of x plus epsilon plus 1/2, that equals the floor of x. But this thing is greater than equal to 0, less than 1. So it has, again, this type, okay? It's just that this epsilon, it's different from this epsilon. This is actually epsilon plus half, but it's just a number. It's just a number greater than equal to 0, less than 1. You can get rid of it. So that would be simply that you have 2 times the floor of x. So this is the right side. So let's look at the left side. So left side is 2 times x, but we have x equaling the floor of x plus epsilon. So I have 2 times x, which is the floor of x plus epsilon. Okay, I'm going to do some algebra inside the first floor notation. So you have 2 times the floor of x plus 2 times epsilon. Now, case 1 is when epsilon is greater than equal to 0, less than half. So 2 times epsilon should be greater than equal to 0, less than 1. Also satisfy this condition. So 2 times epsilon is a number between greater than equal to 0 and less than 1, strictly less than 1. So I can get rid of it in the floor. I get 2 times the floor of x. We're done, okay? Because these two are the same. So we proved the equation for this case. Let's look at case 2. When epsilon is greater than equal to half, less than 1. Okay, well, in this case, the right side equals the floor of x plus the floor of x plus epsilon plus 1/2. Okay, but now this epsilon plus half is actually greater than equal to 1, less than 3/2. So let me write down plus, well, maybe I should just write 1 plus something at time. Okay, So epsilon plus 1/2 is greater than or equal to 1 less than 3/2. So I'm going to get rid of 1. So epsilon plus half, you rewrite it as 1 plus epsilon. Okay, so minus 1 is greater than or equal to 0, less than half. This is our epsilon, our eta. Okay, it's the uh, you subtract 1 from epsilon plus half and becomes some kind of decimal number between 0 and 1. Actually, between 0 and 1/2. But nevertheless, it's between 0 and 1. It's greater than or equal to 0 and strictly less than 1. So you can get rid of eta. So I have this thing. But this is an integer, okay? This is an integer. So that's just that. Yeah, 2 times. All right, so that's the right side. And the left side is 2 times x, the floor of 2 times x. X equals, again, x equals the floor of x plus epsilon, where epsilon is greater than or equal to half, less than 1. That equals 2 times the floor of x plus 2 times epsilon. But now 2 times epsilon is greater than or equal to 1 less than 2. Okay, because epsilon is greater than or equal to half, less than 1. So I'm going to subtract 1. So 2 epsilon minus 1 would be greater than or equal to 0, less than 1. This is our sort of new epsilon. You call it eta, okay? So that equals the floor of 2 times the floor of x plus 2 epsilon equals 1 plus eta, okay? This eta is between 0 and 1. So in the floor, I can get rid of it to floor of x plus 1. So left side, right side, and the right side, left side, their equals were done. Okay, so that finished the proof of the original equation. You probably need to get used to the expression of floor and ceiling, and be able to prove some of the identities. The proof of identities in simple cases would be considered as challenging, and something like this problem would be considered to be advanced. There's a homework problem, which also, I think it's about floor of 3x equals this thing. The idea is very similar, but you need to separate epsilon into 3 cases. Greater than or equal to 0, less than 1/3, greater than or equal to 1/3, less than or equal to 2/3, greater than or equal to 2/3, less than 1. Be very sensitive about greater than or equal to versus the strictly less than. Okay.